So for example, if you consider let's construct the X algorithmically, okay? And what we can do is that we can have n is equal to, for example, 0 to 100, okay? And then we can construct the X that is equal to my TV to the power of n. So what that gives us is X now becomes a 200 by 100 matrix. The first column is just the ones. The second column is X, is my TV. The third column is TV squared, etc., all the way to TV to the 100th power. And I can still let my A to be that. Okay, we already see potentially there might be a problem. It says the matrix is singular to working precision, right? And then my model 4 is still X times A. And now when you plot this, did I get nangs in this model 4? Oh, I get nangs. So let's actually do something a little bit less aggressive. And X is equal to that. And let's actually do a little bit less. 30. Okay. So if we now plot it, so we get a weakly shape like that. So it's this is a tricky scenario, right? The question is this weakly shape real or not real? How do we answer that question? So there are scenarios where you can actually you can look at this closely and say maybe there is actually some weakly over here, right? So in this region of the space, there does seems to be more data that is under here than up here. But the real question is that real, or is just an artifact due to insufficient amount of data? The fact that after you perform the regression, and this goes down a little bit, it's probably a reflection of the fact that in this narrow range of data, there is actually more data down here, right? So is that actually statistically significant, or that's just a random fluctuation in the finite sample you have? How do we answer that question?
Take more data.
Yeah, take more data is always a solution to everything. It's not necessarily going to be always a practical solution though, since it's always costly to take more data, right? So what's the alternative if you cannot take more data? Pardon? Try a different fitting method and see if the same. That's actually a possible solution. It's just usually when you want to decide on the fittings, on the method is good or not, it's hard to compare two methods and see how different they are and conclude on if one method is better than the other, right?
If you do bootstrapping on your original data, then
right. So here is one of the good suggestions coming up is do something called bootstrapping. So this idea, the bootstrapping idea, is basically taking a subsample from your samples. So basically, the general idea of determining whether the fitted model is real or due to statistical noise is you have to split your data. You have to sacrifice how much data you have. you have to split your data into one part that you use for training and the other you use to evaluate how good the model is. So basically, you train your model only on a part of the data, and how good the model is has to be evaluated on the part of the data that the model never sees. All right. So for example, in this case, if we do that, instead of computing my A to be that, you have to take a subsection of the data. For example, 1 to 150, I'm taking 3/4 of the data to perform the fitting of this model. So both X and Y has to be restricted to that range. Okay, and then we can now plot
It's because you take
it should be one of them.
Like that. Sorry, what's the problem you saw?
Because
Maybe. Oh yeah, that's fine. I think I just I didn't do the second dimension. All right. So my model 4 is let's see. I'm going to tell it model 5 is going to be X again times A. So model 5 is now evaluated on the whole set of data. So now if I compute how much error there is on the rest of the data, so instead of summing over the whole thing, I'm going to sum over 151 to end to model 5, 151 to the end. So now it tells me how much error the model 5 has when I have a 30-dimensional polynomial. So how about if I compare that with my 3-dimensional polynomial to see which one is better? So here is now instead of goes to 30, I go only to 3. All right, and I'm going to repeat the procedure of X is equal to this, and A is again fitted using the first 150 data points. And now I just have model 5. Now I have model 6, X times A. And I want to sum over again my model 6. So as can be seen, even with the higher dimensional input parameters, my model actually underperforms, right? Have a larger sum than the model I come up with only 3 polynomial orders. But if you, so this is the error computed on the test data. If you compute the error on the in-sample, the in-sample, which is the sample you use to construct the parameters, it's a completely different story. If you, for example, if you sum up the error of my model 6, which is the 3-dimensional polynomial, versus the 30-dimensional polynomial, you can see that the 30-dimensional polynomial, model 5, has less error than the 3-dimensional polynomial. But in the out-of-sample test we have just did, the model 5, which is the 30-dimensional polynomial, has a larger error than my 3-dimensional polynomial. Right. So this is the procedure we usually have to do to determine what's the complexity of the model we want to use in a statistical learning framework.